Okay, so thanks everyone for joining my talk. I'm going to talk about process memory architectures, in particular some work that I conduct during my PhD thesis related to enabling the adoption of data-centric systems, hardware software support for processing using memory architectures. So really brief self-introduction. So I'm Geraldo. I'm a last year PhD student here in the Safari Research Group. I've been working with Professor Onomutlu since 2017. If you are interested on whatever I'm going to talk about here, feel free to contact me over email. And I do research mostly on computer architecture, computer systems, and hardware security. So the problem that we are going to try to solve over here in this talk is a problem that you might be quite familiar with, which is the data movement bottlenecks that current applications and systems have been suffering today. And data movement bottlenecks might happen in a system for a myriad of reasons. For example, maybe your application does not have enough data locality to make efficient use of the cache hierarchy in your system, or maybe your main memory cannot provide enough memory bandwidth to achieve high peak throughput for your computing resources, or might be that the average trip to go to the memory hierarchy might be too high in terms of latency, and that creates a penalty for your application's performance. And nowadays, data movement bottlenecks have been exacerbated because of a push from the application domain. So applications that become more and more data hungry as we progress over time. A classic example is neural networks, particularly transformers, where we can see that really quickly in a span of only 2 years, we have an increase on 4 times in order of magnitude on the memory requirement to run those transformers models. So here in this plot, for example, you can see in the x-axis that from 2017, 2018 to the current GPT-3.4 model, the model size significantly increased over the years. Another problem from the energy perspective, we see that data movement dominates current systems in terms of memory consumption or energy consumption. So we did this study in Google in 2018, and we saw that in consumer workloads, about 62% of the total system energy was spent on data movement, moving data across the system. And this is not only the case for general purpose systems. We see that in accelerators. So we did again a study with Google where we analyzed neural network models running on the Google Edge CPU accelerator. And over there as well, depending on the characteristics, we saw that a large majority of the system energy consumption was caused by data movement across the accelerator itself. And this might happen, that's happened because of the way that we've been designing systems over the years. So we've been designing systems following this von Neumann architecture, where we clearly divide the system into compute, storage, communication, and computation elements. And now this division led us to have a system where a memory access can take 2 to 3 orders of magnitude more energy than that providing or computing complex operation. And we have been trying to solve this problem over the years, what we call computer-centric architectures, by, for example, designing systems with deeper and deeper cache hierarchies, or systems with more aggressive hardware prefetchers, or fancier memory device like HBM high bandwidth memory chips. However, still we are facing those data movement bottlenecks in current systems. So alternative to alleviate data movement bottlenecks is what we call a paradigm shift, where we are going to employ memory-centric architectures. So the main idea of memory-centric architectures is to do computation where the data resides. And one classic example of memory-centric architectures is what we call processing in-memory. So in a processing in-memory architecture, the computing elements have access to abundant memory bandwidth, shorter average memory access time, and abundant per-array parallelism. All of this because the memory and the compute are integrated together. So the idea of process memory is not new. Since the 70s, academics have been proposed processing memory architectures, and nowadays we have seen those architectures finally reaching the market. And because of this proliferation of processing memory architectures, now we have two types of processing memory architecture depending on how you do computation. The first type is what we call processing near memory architectures, where we add logic near the memory chips themselves. So this might be near the memory controller or near the DRAM bank of a memory chip, or in the logic layer of a 3D stack chip itself. So here, the idea is still quite similar to the von Neumann model that I briefly mentioned earlier, where we still have the separation between compute and memory, but we are going to integrate the compute elements near the memory elements themselves. The second approach is quite different from the von Neumann model. And here, what we call processing use memory architectures, where we are going to use the operating principles of the memory cells themselves to perform some sort of computation. And here, we are not going to have the separation of compute and memory. We are going to use the memory cells themselves for compute. And I'm going to get into details on both of those architectures during this talk, and I'm going to mostly focus on processing using memory architectures, but I want to briefly mention processing near memory architecture, since with what we are seeing in the market nowadays. So as I mentioned earlier, those processing near memory architectures have been proposed since the 70s, but just now recently we are seeing the first processing near memory prototypes reaching the market. So we have processing near memory prototypes for several major companies. For example, SK Hynix have released their AIM architecture, which includes some compute elements near the DRAM banks of DDR6 memories, targeted to accelerate transformer inference. Alibaba has its own architecture as well, where they use hybrid bounded to create a chip to accelerate recommendation systems. We have this French startup company called UPMEM, which releases the first processing near memory architectures, which includes general purpose cores near DRAM banks for general purpose computation. And again, we have a huge push from Samsung, which their UPMEM line, where they again include some computing elements near 3D stack memories to accelerate neural network inference. I'm going to really briefly describe the UPMEM architecture, because we have been doing some research on this engine and trying to improve it inside here in our research group. So this process near memory architecture called UPMEM is a near DRAM bank architecture that targets general purpose computing. And here what we have is some DRAM DIMMs, and inside these DRAM DIMMs you have several of those process memory chips. And inside these process memory chips, what we have is some really simple in-order cores, which are multi-threaded, connected to a DRAM bank for computation. And the integration that follows for the UPMEM pins architecture, but not only for this architecture, also for other processing near memory architectures, as for example the Samsung one that I just mentioned, is a loosely coupled accelerator model, where we can offload some data-intensive computation to these processing near memory chips. So the way that you program those chips, basically following this loosely coupled accelerator model, is by first splitting your data across the processing memory chips. And this model is quite similar to what you do when you program a GPU. For example, you first select which compute kernel you're going to offload, and then separate the data from the host main memory to the data that you're going to compute over in the accelerator. Then you transfer this data to the process memory chips, and then you do some form of caching inside the process memory chip itself to speed up the computation. And finally, we move the data from the process memory chips to the host main memory after the computation is done. So as I briefly mentioned here, but I'm not going to describe in details, programming this type of systems requires non-trivial efforts, because we need to have some underlying knowledge of the hardware so that we can do this data migration from the host memory to the PIM memory. They splitting the data appropriately across the process memory cores, and then launch the computation in its own programming model. So this creates a barrier for processing in memory architectures, and our goal in the work that I'm going to mention next is to ease the programmability of those real processing memory chips by abstracting away the underlying hardware characteristics from the programmer in a programming friendly manner. To this end, we propose this framework called SimplePIM. So the SimplePIM architecture basically provides some standard abstractions to the programmer, so that the programmer can easily deploy processing memory programs. The framework is composed of three main abstractions. Those are C++-like APIs. The first one is the management interface, which provides metadata APIs for the user to allocate data that's going to be later offloaded to the processing memory cores. We have some communication interface API, which allows the user to do some scatter or gather primitives from the data across the processing memory chips. And then we have some processing interface, which applies some common iterators like map, reduce, or zip to allow the user to implement some complex workloads. So I'm not going to get into details on the SimplePIM architecture over here, but basically what we did, we used this architecture to implement 6 real-world applications and deploy these applications in a real UPMEM PIM chip with more than 2,000 PIM cores, and we compare its performance and programming effort to a hand-optimized version of the same code. So we don't need to read this code here, just need to look at how many lines we have here in this example. And here, basically what we have is the hand-optimized histogram version of the UPMEM of user implemented code without using SimplePIM. And then you can see we have several lines of code. And if you use SimplePIM, we reduce significantly the line of code required to implement the same histogram code in a more efficient and compacted way. So to put in numbers of lines of code reduction, by using this type of framework, we can reduce the programmer complexity significantly compared to a hand-optimized code to implement those 6 applications. And because of our framework also uses some optimizations in its back end, we can also provide performance in comparison to the hand-optimized versions, and even outperform the hand-optimized implementations depending on their workloads because of those optimizations that we employ in the back end. So this is also true for a strong scaling analysis, where again we see good scaling compared to the hand-optimized implementations, compare SimplePIM implementation with the hand-optimized implementations, and some outperforming of SimplePIM compared to the hand-optimized code as well. So SimplePIM is available in our GitHub repository. You can download it and use it. And we keep improving on top of SimplePIM for improving the processing near memory programmability. So to this end, we implement this DaPPA framework. Again, the goal is the same, is to provide some sort of APIs to the users to minimize the programming efforts to program processing near memory architecture. So we in DaPPA, we take the idea of template-based programming that we first introduced in SimplePIM, and we extended that by using data parallel patterns, which allows the user to completely ignore or does not need to take into account any of the data movement that needs to happen inside the processing near memory chip itself. So in DaPPA, with the user does not need to specify the communication that is going to happen inside the code itself. The framework automatically distributes and gathers input and output across the processing memory cores, depending on the processing or the parallel primitive that you're going to use in your application. We also have a framework that has 3 components in DaPPA: data parallel pattern APIs, data flow programming interface, and dynamic template-based compilation model. So here I'm going to show quickly how we use DaPPA to implement a vector.product operation. So let's say that this is the target computation, and in DaPPA we have 5 data parallel pattern APIs that the user can use: map, reduce, filter, window, or grouping, and also combination of those data pattern APIs. And this data pattern APIs basically defines what we call a pipeline, where we have several stages and data move across the stages across this pipeline. So the user just define these stages within this pipeline. Note that here we don't define explicitly how the data is going to move. The framework is going to take that automatically into account. And then we use this template-based compilation to generate the UPMEM code transparently from the user and execute that code in the processing near memory system. So again, we use a real UPMEM pin system to evaluate DaPPA with 6 real-world applications. And again, we compare the execution time of using DaPPA versus using hand-optimized versions of the same applications. And we also compare the programming complexity in lines of code of those 2 implementations. So here we have the performance. As you can see, for some workloads, DaPPA can provide performance improvement because it implements some optimizations in the back end. And from other applications, we see similar performance to that hand-optimized version compared to the DaPPA implementation. In terms of lines of code reduction, we see significant reduction in programmer complexity because we fully abstract away the hardware components from the programming model itself. So compared to SimplePIM, DaPPA provides 3 main benefits. Is a high first is its high abstraction level, because here, as I mentioned earlier, we don't need, the user does not need to specify the communication patterns that it's going to be requiring the application. We have support for more parallel pattern primitives, which allow the users to implement more workloads, and we implement further optimizations to allow concurrent execution of host code and processing near memory code transparently from the user. So basically, here we conclude that DaPPA improves the state-of-the-art programming from frameworks for PIM. So DaPPA is available on archive, and now I'm going to go back to the processing using memory architectures. So just as a reminder, in processing using memory architectures, we are going to use the analog operating principles of the memory cells themselves to perform computation. And in particular, in this talk, I'm going to talk about processing using memory architectures, using DRAM architectures, where we are going to use DRAM cells for computation. And for what I'm going to show next to not look like magic, I need to bother you a little bit with some DRAM background. So really briefly, a DRAM chip is organized as a hierarchy of components. At the top level of this hierarchy, we have what we call a DRAM mat, which is a 2D array of DRAM cells. Those DRAM cells are horizontally connected to word lines and vertically connected to bit lines. Bit line shares a local simplifier, and row shares a local row decoder. In the next level of the hierarchy, we have what we call a DRAM subarray, which is a collection of DRAM mats, which shares a global row decoder and a global word line, which propagates across all of the DRAM mats in the DRAM subarray, and a global simplifier, which connects the DRAM columns to the I/O interface to move data from the DRAM mats to the memory channel doing read requests. So the memory controller issues 2 main operations to read data from a DRAM subarray. The first one is activate. So when the memory controller issues activate to a given DRAM row, that DRAM row first is asserted, connected the DRAM cells to the local bit line, and this connection generates a perturbation in the voltage level of the local bit line, which is initially precharged to a half of VDD. This perturbation is then sensed by the local sense amplifier, and the data is latched and amplified to a logic 0 or a logic 1, depending on that direction of that perturbation. Then the memory controller can issue column requests by issuing read requests, which reads portions of the data that was latched in the local simplifier to the global simplifier and eventually to the memory channel. So prior work has shown that we can use these analog operating principles of the DRAM cells to perform several operations. So we are going to start really simple in this talk, and progressively we are going to get more and more complicated. So we're going to start by doing in-DRAM row copy operations. Here, basically, I want to tell my DRAM chip, copy a source row to a destination row without the intervention of the DRAM of the memory of the CPU itself. So how this works? So basically, we issue a activate commands to the source row, and this works exactly as I just mentioned in the background. The data that is latched in the source row is going to be latched in the local sense amplifier, and the data is going to be amplified either to a logic 1 or a logical 0. But then we are going to issue another activate to a destination row, which is going to connect the DRAM cells in that destination row to the local sense amplifier and the local bit line, which had previously held the data in this that was activated from the source row itself. This is going to allow the local amplifier to drive the data that was latched from the source row into the destination row, hence doing that in-DRAM row copy operation without moving the data to the DRAM cache themselves. So by doing this, we can improve performance and energy of in-DRAM row copy from 1046 nanoseconds to only 90 nanoseconds, and improve energy from 3.6 microjoules to 0.04 nanojoule, because we're not moving any data outside the memory chip themselves for this in-DRAM row copy. So we can use the similar approach to do a little bit more complex operation. Now you're going to do majority of 3 operations by activating 3 DRAM rows at the same time. So when you activate 3 DRAM rows at the same time, the DRAM cells on those 3 DRAM rows are going to simultaneously perturbate the local bit line. Sorry, and since what we have in the local sense amplifier is a differential sense amplifier, this differential sense amplifier is going to pull the voltage level to that of the majority of the voltage level stored in the 3 DRAM cells at the same time. So in this example here, the cells have 1, 1, 1, 0, and 1, and the majority of that is 1. So by doing that, again, we can significantly improve the performance of doing Boolean operations. So we can set one of those rows to do either Boolean AND or Boolean OR majority of 3, if you don't want to set one of those rows. And then we can reduce the energy consumption of doing Boolean operations in DRAM from 137 nanojoule per kilobyte to 3.2 nanojoule per kilobyte using this approach. So before, when you propose these works in Safari, we propose them mostly on simulations. We show using SPICE models that those operations are feasible using DRAM chips. But recently we've been conducting some experiments using commodity off-the-shelf DRAM chips, and we saw that commodity off-the-shelf DRAM chips are very capable of a subset of those in-DRAM operations as they state today. So we saw that commodity of DRAM chips can simultaneously activate up to 48 DRAM rows in 2 neighborhood DRAM subarrays. They can perform NOT operations with up to 32 output operands, and they also can perform up to 16 input NAND or NOR operations without any modifications to the DRAM chip itself. We are just going to operate those DRAM chips a little bit different by violating some DRAM time parameters. So what we do in our testing here, we have this FPGA-based infrastructure, which allowed us to have fine-grained control over DRAM commands, times, and temperature. And we tested 256 DDR4 chips for 2 main major manufacturers, so SK Hynix and Samsung, and those covers different die revisions and chip densities. So unfortunately, we cannot activate multiple DRAM rows as we want in commodity off-the-shelf DRAM chips because it's not a legal operation. but we can emulate that multiple row activation by violating the DRAM time parameters between two consecutive memory activations in the DRAM chip itself. So by doing so, we can have commodity off-the-shelf DRAM chips to perform functionally complete Boolean NOT, NAND, and NOR operations, up to 16 AND, NAND, or NOR operations, with a significantly high success rate for some of those operations. So up to 94% success rate. And here we have a success rate because, again, we are doing some illegal operations in those commodity off-the-shelf DRAM chips. We also had studied how this success rate varies if you vary the data pattern and temperature of the DRAM chips, and we saw that it only slightly impacts the reliability of those operations. And here, what we want to show is that those processing using memory operations is not something extremely futuristic that can only be achieved in simulation. Commodity off-the-shelf chips, as they state today, can already perform computation. So we don't need to only treat those memory chips as a media, as a form of media. We can actually do computing on those memory chips as they state today. So if you are interested on those initial works, I invite you to check our initial paper on in-DRAM row copy and in-DRAM Boolean operations. But now we are going to try to tackle some of the challenges of making those operations feasible in current systems. So we can do those in-DRAM row copies and in-DRAM majority operations, and this is really nice. But if you want to fully support processing memory in current systems, you need to address a myriad of problems because this is we are moving from one paradigm to another. So the first problem is a given application. How can I know if this application would benefit for this type of processing in-memory execution? Second, how can I use those processing memory primitives, those in-DRAM row copies and in-DRAM majority operations, to implement something more complex that my application is actually going to use, like in-DRAM addition or in-DRAM multiplication operation? Also, how can I generate code that can be compiled to my processing memory engine? What is the type of operating system support that I need to allow me to execute processing memory operations? And how, if I use these processing memory chips or as I use my main memory as accelerator, how should I deal with problems as, for example, data coherence and data consistent? And then in this talk, I'm going to briefly talk about some of those challenges quite briefly, and in the end, we're going to conclude on what is next. To start with, frameworks for processing memory. So our goal in this work, which is called SIMDRAM, is to extend the operations that we can do in DRAM by composing those in-DRAM row copy operations in more complex operations like addition or multiplications without modifications on the DRAM architectures themselves. So to this end, we propose this framework called SIMDRAM, which is built on two main ideas. So the first main idea is to use a vertical data layout for computation. So in your current system, if you have a data word, this data word is going to be spread horizontal in a single DRAM row across several DRAM columns. However, if you want to do some more complex operation like addition, and you want to implement something like a RIP carry header, you're going to face a problem that you need to move data from one bit position to another bit position, for example, in a carry propagation. However, there is no connections across different DRAM columns in a current DRAM chip. So you would have to include extra area to allow connections across the different DRAM columns. So instead, what we do is we just store the data word in a single DRAM column spanning multiple DRAM rows. By doing that, we can implement implicit bit shifting operation because we can just do in-DRAM row copy from one row to another, which means from one bit position to another bit position, and also enable some massive parallelism. So now we can see a DRAM subarray as a single structure multiple data engine where each column is a SIMD lane. So the second approach that we are going to use is majority-based computation. So using majority-based computation, since the primary primitive that we do in DRAM is in DRAM majority, we can achieve higher performance and lower energy consumption compared to using regular Boolean logic for computation. So based on this, we propose this framework which has three main steps. So the framework takes as input a desired operation is in AND or NOT form, and then generates equivalent optimized version of the same circuit using majority NOT gates, which is what you're going to execute in DRAM. And then it maps that majority operation into a sequence of in-DRAM row copies or in-DRAM majority operations in what we call a microprogram. This microprogram is just a recipe that tells my DRAM chip how it should implement that majority NOT logic. Then we store this microprogram in main memory for future use, and we add a new CPU ISA instruction to allow the user to interface with this operation. And then the third step, doing the execution, the user uses that new instruction in this code, and then we implement a control unit in the memory controller, which fetch that microprogram from my memory and triggers the in-DRAM row copies or in-DRAM majority operations to realize that majority NOT logic in DRAM chip itself. So I'm going to illustrate how this works using a book bitwise addition operation. So let's say that we have two vectors, vector A and vector B. All of those vectors have as many operands as DRAM columns in the DRAM subarray, so 65,000 operands, and each operand is only 1 bit of data. And here you're going to add those bits. So in A we have only ones and B only ones, and you want to add 1 plus 1 and get 2 in the end. So the way that this is going to work, first SIMDRAM is going to take implementation of either. So here is a rip carry either. And in the first step, we are going to use that majority NOT equivalent to generate a majority NOT version of the same circuit to generate the addition. Then the SIMDRAM framework is going to traverse this majority NOT graph and issue in-DRAM row copies and in-DRAM majority operations, triple row activations to realize this operation in DRAM. So first we issue a triple row activation involving row A, B, and carry in, and this is going to generate the majority of 1, 1, and 0, which is 1, and the data is going to be stored in a different DRAM row, which is the carry out row. Then we move to the next majority cell, which involves activating row A bar, B, and carry in, which is going to generate the majority of 0, 1, and 0, which is 0, and this data is going to be stored in the temporary row. Finally, we issue the majority of A and the two previous majority operations, which is going to be a majority of 1, 0, and 0, which is going to give us 0. So in the end, we have in the carry out row and in the sum row 1 and 0, which is 2, which is the result of the addition operation that you want to realize. And note here that even though we have this notion of this majority NOT graph in the bottom of the slide, we don't have a majority gate. We are not using transistors, extra transistors in the DRAM chip itself to realize this computation. We are just issuing those triple row activations to realize that majority operation inside the DRAM chip itself. So basically, by doing so, we transform a DRAM subarray in a very wide bit zero SIMD engine. Again, where each column in the subarray becomes an independent SIMD lane. So we evaluate SIMDRAM in simulation, and we compare it to a CPU, a GPU, and the prior state-of-the-art processing in-memory computation. And we use this framework to implement 16 complex in-DRAM operations, including addition, subtraction, division, and multiplication. And we use those in-DRAM arithmetic operations to accelerate 7 real-world applications, including some neural networks. And really briefly, we saw that by doing computation, those 16 operations in DRAM, we see significantly improve in terms of throughput compared to the CPU and the GPU, and also sorry,
Geraldo, sorry to interrupt, but we need to start. Can you please start wrapping up because we are running out of time.
I'm going
thanks
to
a lot. Thanks a lot. Yeah.
And then we can also improve energy efficiency compared to the CPU, GPU, and embedded, and also have performance improvement for those 7 real-world applications compared to those 3 baselines. So follow-up work shows that they can use this processing using DRAM addition multiplications operations to accelerate transformer neural network models. Basically here, the idea is to accelerate the pointwise vector operations using similar approach that I just mentioned, and and then use processing near memory architectures to do the final reduction step inside the DRAM chip itself. And by doing so, the authors of this paper called TransPIM can significantly outperform GPUs for 3 neural network models. So I'm going to skip those slides here. The main idea is that we can do these in DRAM arithmetic operations, but we still cannot do in DRAM transcendation functions. So those being functions like sine, cosine. And to do that in DRAM, those sine, cosine functions, we use an old idea, lookup table operations, where we use the DRAM chip itself to store multiple copies of those predefined lookup table operations, and we define a new operation called Pluto row sweep, which goes through that lookup table and generate matches inside the DRAM chip itself doing the computation. Doing that, we can accelerate. We provide 3 designs of in-DRAM lookup table operations, which have different trade-offs in terms of performance, energy efficiency, and energy efficiency, and we see significantly improved for 7 real-world applications that requires those transcendental functions by doing the implementation in the DRAM chip itself, and also significant energy consumption reduction. To wrap up really briefly, we further keep extending those processing using DRAM substrate and in other execution models. So we saw that the very wide SIMD execution model that I mentioned in the previous slides generates some SIMD underutilization problems, and we try to solve this issue by segmenting the DRAM word line, hence allowing us to do computation in different DRAM mets in a multiple structure, multiple data execution model. So you're migrating from a single instruction execution model to a multiple instruction execution model. This also allows us to move data across the DRAM mets, allowing us to do in-DRAM vector reduction operation, and it also allows us to use compiler substrates to auto-vectorize code and generate code for this processing using DRAM engine. This effort is called MIMDRAM, where we provide those hardware modifications to the DRAM subarray, and also software compiler support that generates codes to processing using DRAM architectures. And also we provide virtual memory and operating system support to allow us to map data properly across the DRAM chip themselves. Again, we evaluate this in simulation with 12 real-world applications, and we see significant energy efficient gains compared to CPU, GPUs, and SIMDRAM. So to finally wrap up, in this talk, we introduced processing memory architectures and several system challenges of adopting those processing memory architectures, and we can address each one of those challenges one at a time, and hopefully fully solve those data movement bottlenecks problems that we are seeing in current applications. So if you are interested in processing memory, we have a class in ETH that we discuss those processing memory architectures in more details, and we also keep giving tutorials on processing memory in main conference. We just gave one in micro and is fully available online, and we have a follow-up one in PIPOP in Las Vegas in 2025. And then we are going to have our first memory-centric computing systems workshop happening in ASPLOS in March, and soon you are going to have the call for papers if you are interested in submitting or your work related to processing memory to this workshop would be great. All of what I mentioned here is available in our website, and also we have our efforts on making our simulation infrastructures and testing infrastructures fully available and open source in your GitHub link over there. And if you are interested in processing memory and this is new for you, we have this Spoon Book chapter that highlights several of those system challenges that I just briefly mentioned in this talk and we have a follow-up coming soon in the beginning of 2025. So thank you very much. I'm sorry if I'm a little bit over time. Hopefully that this was interesting for some of you, and I'll be glad to take any questions.
Thank you so much, Geraldo. We actually have a virtual memento for you. So I'll just project it 1 second.
Sure.
Questions? Okay. 1 second. Also, we'll open the floor to the questions. 1 second.
Thank you very much. I wanted to know the power comparison or power dissipation comparison when you shift a set of, say, instructions from ALU-based operations to the processing using memory architecture. Have you done any comparison? Because I see energy efficiency, but I don't see anything like a comparison there. Like why we should go for processing using memory when we consider power.
So I guess the question is about the power dissipation of those processing memory chips, if I understood correctly. So the main limiter in terms of power when you have a data-intensive application is the power dissipation of the memory channel itself. It's not the gates itself that's going to dominate the power breakdown of your application. This is one main thing. So if you can avoid moving data through that power-hungry memory channel, you're already going to save a lot. And when you look about the logic itself of processing base versus memory-centric base, the memory chip themselves are quite power restrictive on what you can implement. So you're never going to see a GPU inside your memory chip itself because you cannot dissipate the thermal issues that the particular chip would require. So what we see, particularly in the industry right now, is that the logic that you use is used for processing memory chips is quite simple, and they operate at very low frequency, not necessarily very low, but low frequencies compared to process-centric, and also low. And because of that, they require less power dissipation. So usually, when you're designing a processing memory chip, you take that restrictive power budget that you have in the memory chip itself into account. So because of that, the gate itself is more power efficient compared to a CMOS base or a processor-centric base approach. So I don't know if I fully answered the question.
I think that's it, Geraldo.
Yes,
thank you so much. Can you stop presenting if possible?
Sure. Thank you very much for the questions and for the attention.